Well, good morning, everybody, and welcome to our April edition of the Broadcast Engineering webinar series. This is a series of technical seminars. It's actually put on by the ABA Engineering Academy, and it's a joint venture of the Alabama, Georgia, and South Carolina Broadcasters Association. And we produce these each month on the third Tuesday of each month, and we send out emails and constant contacts letting everybody know that these things are coming up. So we have a good number on the call already today, and I would like to ask all of those that are participants or attendees, if you would don't mind to mute your audio and your video. That'll cut down on the clutter. Plus, I was told it also helps on bandwidth. And sometimes we have a bottleneck on the bandwidth or something. Our co-host today is John George, and let me see if I can get off the share here and let John come on. Hey, John, how you doing?
I'm doing great today, and I hope everyone else is.
Are you out in a field somewhere?
Yeah, it's a background shot of one of the AM sites that I deal with from time to time down in Florida. So you just don't see the alligator right now.
Oh, okay. I just saw you there, and I was wondering what the were you doing out in the field. So, John, I'm going to let you introduce our special guest for today.
Okay, good. And I will make one mention, Larry, before we introduce Paul Shulins today, that in case you didn't get the emails that I know Larry sent out and I sent out, there was no FEMA IPAWS test yesterday at 11:01 a.m. Eastern, let's see, 10:01 Central. Uh, there was some technical difficulty. It seemed to affect the Sage boxes and maybe some DASDAC boxes, but not all of them. So they're looking into the issue. So just remember when you go to check your operator logs at the end of the week that you note that you did not receive the test on your log as you should.
John, I got a email last night from Al Kenyon with FEMA, and they had moved over to a new server. And it's usually when you do that, something gets a little wacky, and there was some XML stuff that was different, and apparently that was what the problem was. So they're working on that.
Yeah, I saw that same note, and it appears they had it corrected, I think, by the time it hit the mountain zone and the West Coast. So it's probably corrected by now. Today's discussion and presentation is on thermal imaging using drones for broadcast engineers. It's presented by Paul Shulins. Paul is president of Shulins Solutions, a radio and TV broadcast consulting firm based in Andover, Massachusetts, where it's still cold and occasionally snowing. Uh, he specializes in remote control solutions, studio design and construction, antenna protection systems, and ratings metrics. Previously, Paul had joined Burke Technology as Vice President and Chief Technology Officer in 2017. Prior to joining Burke, Paul had been Director of Technical Operations for Greater Media's Boston, Massachusetts 5 FM stations for 29 years. He's been working as a chief engineer for 40 years. He's been responsible for planning day-to-day management of one of the first major studio consolidations in '98 for Greater Media in Boston. He's designed and constructed many custom on-the-air playback systems, technical facility monitoring, and control systems. Paul's a member of the Society of Broadcast Engineers and held the SBE Radio Engineer certification since 1982. He's also a member of IEEE Broadcast Technology Society and co-chaired the BTS Broadcast Symposium for several years, and most recently elected by the Broadcast Technology Society ADCOM Committee as a distinguished lecturer. Paul has presented numerous papers at IEEE Broadcast Symposium meetings, the NAB Broadcast Convention, and NAB Radio Show. He's also a frequent contributor to Radio World Magazine, authored several chapters in the 11th edition of the NAB Engineering Handbook. He served as an elected member of IEEE Broadcast Technical Society's Administrative Committee for 3 years, and he's vice president of IEEE Broadcast Technology Society. Paul earned a Bachelor of Arts from University of New Hampshire System in 1979 with majors in physics, chemistry, and natural science. He's a private pilot, enjoys astronomy, skiing, and photographer, and he operates his Arizona Observatory remotely, collecting deep sky images. And that last line I just love, because if you've never been to the desert of Arizona, you've really missed out, because you really can experience true darkness and actually see the sky there without light pollution. So, Paul, I'll turn it over to you.
Hey, well, thanks very much. I appreciate that kind introduction, and I'm truly honored to be here today. Thank you all for your time, and this should be a little bit of fun. Let me see if I can share my screen here. So let's put that on. And F5. There we go. Can everybody see that okay?
Yeah, we got it.
Okay, great. So good morning, everybody. Thanks again for having me. Yeah, I've been, as we said, I've been in the broadcast industry for a while. My main background is radio engineering in Boston for Greater Media when they existed. They were sold a few years ago, and then I went to work for Burke, and I've been into remote control stuff a lot. That's kind of what I really like. And by the way, with the astronomy stuff, I'm really hooked on that. And I'm actually planning to relocate to Phoenix next month, as a matter of fact. So I'll have more of those great dark skies. Unfortunately, there's light pollution encroaching on so much of this country, and it really destroys a lot of viewing of the Milky Way and deep sky objects. So I'm kind of passionate about that, but that's a subject for another day. So I came here to talk a little bit about my business and what I'm doing here with thermal imaging, and how that is new to the broadcast industry in a lot of ways, especially using SUAS or drones for taking images of transmission lines and towers and antennas. And I wanted to share with you a little bit about my experience over the last year and a half with this kind of technology, and how useful it's been, and some of the limitations and that kind of thing. So I'm going to go through this as efficiently as I can, and I'll end up pausing a few times for questions. And then, of course, at the end, hopefully we'll have a few minutes for general questions and answers. So let me talk a little bit about infrared radiation, what it is, and when it was discovered. And again, this gets back to astronomy a little bit. William Herschel in 1800 discovered what infrared radiation was. Of course, he was a famous astronomer, and he was also a composer. But he used sunlight and a prism, and he noticed that the prism broke the sunlight up into different colors. And what he really discovered for the first time was those different colors had different temperatures associated with them. When he measured the color of, or the heat from the different colors of the spectrum, he noticed that the red light was warmest, and even an area that he couldn't see beyond the red light was even hotter. So this led to the science of thermography. This guy also, as I said, was an astronomer, and he discovered Uranus, the seventh planet from the sun, in 1781. So infrared is classified as electromagnetic radiation. Its wavelength is longer than visible light, and generally we can't see it with the human eye, because our eye is not sensitive to that wavelength. But anywhere from 700 nanometers to 1 millimeter is the wavelength that we're talking about here. However, there's no hard limit as to what we can see with our eyes. Our sensitivity drops off smoothly at about 700 nanometers. And some sources longer than 700 nanometers can be seen if they're sufficiently bright, and that can create a danger to eyesight. So that's why infrared heating and exposure to your retina can be dangerous. So we couldn't talk about infrared without understanding what emissivity is. And emissivity is actually a measure of how efficiently an object radiates heat. In other words, how well the surface of an object tells the truth about its temperature. And so there is basically one scale to define emissivity, and that scale ranges just from 0 to 1. In general, if the emissivity of the target that you're trying to measure is below 0.5, you're not likely to be able to really get an accurate temperature measurement. And in these cases, you might consider needing ways to increase the target's emissivity. And of course, this is one of the challenging factors that you need to be aware of, especially in an uncontrolled environment when you're taking temperature measurements. But if you understand what you're doing and you have the proper training, it can be properly compensated for. So this slide shows a picture of a couple of paint cans, and those visual images on the left are taken with a standard visual camera, and the right one is with an infrared camera. And you can see there's a piece of electric tape on the cans, and that electric tape has a different emissivity than the can, the silver shiny surface of the can. So basically, this slide is demonstrating that you can't really get an accurate temperature from a low emissivity value because the truth won't be told in terms of what a meter is going to see. So one trick would be, when you're dealing with like a copper transmission line, is to be able to put a piece of tape or some kind of known surface that is going to have a known emissivity, and then you can calculate the actual temperature, if that's what you're really interested in doing, by putting tape on there. So for example, with a transmission line or an elbow or something like that that's heating up, you may want to put a piece of electric tape on it when you shoot that with a infrared camera, and that's going to give you a much better idea of what the temperature is if you have the meter calibrated properly. This is an example of emissivity values for different types of materials, and you can see how low either polished copper, brand new copper is. That's a 0.05 value for emissivity, which is basically not going to give you any reflected heat. However, you look at formica and food and organic materials, fiberboard, all those other kinds of materials you can see are dramatically different. So it's important to understand what you're looking at if you're looking to make accurate measurements with a thermal camera. But it's not always important to get those accurate measurements in terms of the actual numbers. And I'm going to talk about that in a few minutes here. But basically, there are qualitative and quantitative measurements of looking at thermal images. And of course, qualitative is using thermography skills and training to evaluate the thermal images visually. Such examples include looking at a big solar array panel, rooftop, and of course, in our case, where we're talking about applications for this industry, broadcast transmission lines and antennas. On the other hand, quantitative measurements or numerical measurements report using calibrated instruments, always in a controlled environment. What I mean by a controlled environment is generally indoors, where there's no wind and solar loading and other factors that may affect what you're seeing. Examples of quantitative measurements would look like taking a picture of a running motor, electrical panels, circuit breaker panels, that kind of thing. And of course, human subjects, we've all seen with the pandemic, you go into a store sometimes and they want to take your temperature with a thermal camera. Qualitative measurement is not going to cut it. You just can't tell whether somebody's at 98 degrees or 102 degrees, but quantitative will give you that exact measurement to tell whether someone's got a fever or not. So how it works, how a camera works is basically there is a vanadium oxide detector or a silicon resistor that the infrared energy is hitting. And basically when that infrared electromagnetic radiation comes into contact with the sensor, the electrical resistance changes. And these changes in resistance are, of course, measured and processed into digital signals. And what we end up with is a nice picture on the display that shows the thermal contours of what you're looking at. So what do we use it for? What have I been using it for? Basically, visual tower inspections, a drone is used for, infrared scans for heating, RF signal measurements, drones are used for, and thermal imaging of AC power panels, which you'd use a handheld gun for. So these are some of the examples where I'm just showing examples of where SUAS and infrared are used either together or separately in broadcast engineering applications. So why would we want to use this infrared imaging? Well, it allows us to detect electromagnetic radiation that's not readily visible in a traditional photograph. And it kind of gives us an extra sense of what's occurring around our electrical RF systems, because as humans, we don't have that kind of capability with our God-given senses. So this sixth sense here shows us a whole new world of energy that's out there that may or may not be beneficial to us in terms of heating. We want to know if we're losing energy in a place that we don't expect or want to be losing energy in. So for infrared, here are the main applications: tower transmission lines, broadcast antennas, RF patch panels inside, RF combiner modules, motorized RF switches, and of course, I already mentioned electrical AC power panels. So I'm going to pause here for a second and see if we have any questions, because I don't want to get too far behind here. So let me just pause and open the floor up for a minute. If there's anything that I've said so far that people have questions about, I'll try and answer them.
Yeah, if people would like to, as he's talking, if you'd like to ask a question, you can use the chat menu down at the bottom of your screen. You just click on chat and type in a question, and we all can see the question, and he'll be happy to answer that.
Okay, and I'll try and figure out how to bring up my chat window.
They're on the down on the screen, down on the bottom or the top, and we just saw one pop up. Says somebody asked, what is the emissivity of electrical tape?
Oh, okay. That number is very high. It's almost 1, which means it's almost a perfect emitter and absorber. I don't have that number in front of me, but it is very high. So it's appropriate to use if you're going to be trying to look at a specific temperature using quantitative measurements. Okay.
Yeah, that was the only one that popped up at the time, but anybody would like to ask something, just type it in and we'll relay it to Paul. Okay,
great. Thanks. I'll continue to pause every once in a while here so we don't get too far behind. SUAS, I've been using that term. It means small unmanned aircraft system. So it's basically a drone, but it's more than a drone. It consists of the unmanned aircraft, which is the drone. It needs to be defined as weighing less than 55 pounds. And it includes the drone and the system on the ground connecting the operator to the drone. And it also includes the operator. So there's really 3 pieces to an SUAS because it's a system. So it's the drone, it's the communication device, and it's also the operator on the ground. So these drones allow us to, of course, inspect areas on a broadcast tower that are not easily accessible. In general, it ends up being safer and less expensive than hiring a tower crew. And some of the advantages are that it gives us the ability to fly in a wide range of weather conditions. I've used my aircraft in pretty windy conditions and also in rain. So it depends on the type of hardware you have. And I'm going to talk a little bit about what I use. But generally, these conditions are not conducive to humans climbing a tower. So basically, it gives you a little bit more flexibility in terms of scheduling these kind of inspections. Also, the ability to fly on short notice, especially during the repack. It's been hard to get a lot of tower crews scheduled, so the drone can be deployed pretty quickly. And of course, the perspectives you can get from the drone, looking at different angles, even flying above the tower and looking down on the tower, are things that you can't really get from a tower climber. So there are some definite interesting advantages to using this kind of technology. But there are some regulatory and operational considerations that have to be dealt with. First of all, if you're using this for commercial purposes, you need to employ a pilot that is licensed by the FAA. Part 107 is the actual FAA part that defines commercial drone operators, and there's a special license. You don't have to be a private pilot to be a Part 107 pilot, but you do have to understand airspace restrictions and a whole bunch of safety stuff, rules and regulations that they make you take a written test for. So that is one thing that you need to be aware of if you're going to do this commercially. Also, it always requires a second person to act as a spotter. I've learned from flying these aircraft that it's pretty stressful. I mean, you've got a lot of money tied up in the hardware, not only the drone itself, but the payload, which is the infrared camera, which is very expensive, and also the visual camera, which is not cheap either. So you're looking to make sure that you're getting, the right kind of data coming down and you're saving it properly. But you also want to make sure that you don't run the thing into the tower or guy wire. And that's why the second person sitting there, with his eyes always on the aircraft and next to the operator, so that they can act quickly if something starts to go awry. Because if you're looking down at the controls, you really don't have a great sense of where the drone is, even though you can look at the real-time picture coming off it. It doesn't give you a good idea of whether you're getting close to a guy wire or an antenna that's sticking out. So that's why a second person is required. Depending upon the location and the airspace, most often it requires the FAA and local approvals to be able to fly above 400 feet above the ground. So I happen to use a consulting firm that's hooked up with the FAA that can get me waivers to be able to fly in certain areas that are close to airports or close to municipal, cities and areas that are tough to fly in. If you're up in North Dakota and you're not close to anybody, it's usually Class G airspace as defined by the FAA, and basically you don't need any authorizations. But for the most of the country and most of the places that I've been flying, like for example here in Boston, where it's very populated and crowded, I'm almost always needing to get FAA waivers and approvals. And by the way, these restrictions also are geofenced into all the hardware in drones now. So if you own a drone, you probably know this already, but you cannot even take off usually in restricted airspaces unless you've gotten that authorization as a software update downloaded to your controller. And that usually is only good for a certain period of time and a certain geographical location. So it's pretty well locked down. Also, with regard to the equipment, liability and hull insurance are a must. So that's something that I just deal with. I'll tell you, the investment I have is north of about $40,000 in the aircraft and the imaging and the training. So it's worth protecting with insurance, of course. The last thing you want to do is crash the drone and send it back in 100 pieces and hope they can put it back together. So having that insurance is a good feeling. So when can you fly? Well, not in all conditions. you need to have the wind cooperate. And that varies with the type of equipment you're using and of course the skill of the pilot and your comfort level. However, I will say that I've flown with gusty conditions and winds in the 20 to 30 mile an hour range, and I've had good success. So the larger the drone, the bigger the propellers, and the more experience you have, the more flexibility you have in terms of wind and the types of conditions you can fly in. Of course, it requires ceiling and visibility clearance. I flew a couple of times when the ceiling was below the top of the tower. And of course, one of the requirements is that you be able to have line of sight visual contact with the drone all the time. So I couldn't go up to the top of the tower, but what I needed to look at was below the fog line, and that worked out okay. But obviously, if you're going to look at things with a visual camera or an infrared camera for that matter, you need to make sure that you have the visibility and the ceiling clearance. In terms of the time of day to fly, dusk or dawn is best. So after sunset or before sunrise, usually when the sun is about 6 degrees below the horizon is a good time where you're going to still have enough light to see what you're doing, but you're not going to get any of that solar loading. And as you can imagine, solar loading interferes with really what you're trying to do if you're using thermal imaging, because you've got all this radiation from the sun that is adding to the heat of what you're trying to image. And basically, it doesn't make it impossible, but it lowers the signal to noise ratio of what you're trying to achieve. You're looking for basically contrast between different areas on, say, an antenna or a transmission line. And if the sun is beating down on what you're trying to image, it's going to decrease that difference and thereby decrease your signal to noise ratio and allow you to see less of what you're really looking for. The reason why you don't want to fly too late is either FAA regulations not allowing you to fly too late because you don't have the right lighting equipment on the drone, or just danger. You don't want to be able to hit a guy wire or get too close to the tower if it's pitch dark out. And of course, if you're making thermal measurements, you probably want to have all the stations on the air at the time. RF interference cautions. So you might wonder if you're imaging and you're getting a drone close to a high power TV or radio antenna transmission system, what happens, and do you get interference with the control signal coming from the ground to control the drone? And the answer is you can. However, buying equipment that's properly shielded and using the right techniques can help you get around this. There is a technology called RTK, and I'll explain what that is in a second. But basically, that helps with the stability of the control signal to the drone. You want to fly as far away from the radiation elements as you can and still get the resolution that you need to. So you don't want to be so far away that you can't really get any good information out of it. But then again, you don't want to be right on top of the antenna so that you have damage from radiation or loss of control or anything like that.
Paul, here's a question that came in that addresses what you're talking about. It says, how do you keep the RF out of the camera optics when operating around high power antennas?
Yeah, that's a good question. And basically it comes down to the shielding and the makeup of the payload, the sensor. The type of equipment I'm using, which I'm going to get into in a couple of minutes, is very well shielded, very well made, and I haven't had any problems with RF getting into that. What I have had problems with is RF getting into the control signal going back and forth between the joystick and the drone. And not that I've ever lost control of the drone, but sometimes I've gotten some weird indications on my display about battery power and that kind of thing. But basically, if I was going to answer that question, I would say get a camera that's well built, and the types that I have purchased, which I'll show you in a second, haven't had any problems. And I've been imaging in about the worst conditions you want to in terms of RF. We've had 7 or 8 high power UHF TV stations on roughly 100 kilowatts TPO. And I don't know what the ERP was, but it was, probably close to a megawatt. And I was maybe 20 or 30 feet from the antenna and was still able to image. So there you go. It's possible to do if you have the right equipment.
Do you have a problem with the new ruling that came out about the red LED lights? They're requesting people that have red LED lights to actually put our emitters because of pilots flying with night vision goggles. They can't see the regular red LED, so you have to put our emitters. Does that cause a problem?
I heard about that, and I honestly can't say because I haven't run into it yet. That's going to be interesting. Thank you for mentioning that. I don't have an answer because I haven't run into it, but I think if you know where it is, you probably can compensate somewhat for it and not worry about about it because it's a beacon, but it may detract from looking for a problem right adjacent to the beacon, right? Because the beacon might be very close to the transmission line, so that could cause an issue there. So interesting thought. Thank you. Anything else?
No, that was all the questions we had at the time.
Okay, thank you. So anyway, the next point I was going to talk about was using the appropriate focal length lens for the camera. In most cases, in fact, probably all cases, the types of payloads that go on the drone, those cameras do not have interchangeable lenses, as at least the infrared ones don't. So it's important to choose an appropriate focal length for the application, in this case, imaging towers, antennas, and transmission lines. And using caution for guy wires, of course, and other obstacles, and never flying over people or animals. That's part of the regulations. So I mentioned RTK. RTK stands for real-time kinematic positioning, and it is an enhanced satellite navigation techniques used to help with the precision of the positioning of the drone. And if you look over here, you can see the drone in the middle. There's the guy with the controller, and he's sending a signal to control the drone. But we also have the satellite, which has GPS information coming down directly to the drone. But this base station, which is the RTK base station, is located several hundred or even several thousand feet away from the operator. And this also collects GPS data and also has a magnetic compass information in it. And it transmits this information to the drone independently of the individual controlling the drone. The net effect here is that the drone has extra high precision accuracy down to several centimeters. And this bringing the magnetic compass down also makes the drone less vulnerable to losing its orientation and positioning, because generally the magnetic compass doesn't do very well in high RF fields. So we keep this down here on the ground and we transmit the information up to the drone. And the end effect is it gives much better stability to the drone. And this also helps with wind conditions. If it's very windy out, this helps stabilize the drone. When I say a couple of centimeters accuracy, that is the accuracy of knowing where the drone is. It doesn't mean that the drone is going to stay within 2 or 3 centimeters of where you put it, but at least the positioning is well known to within that kind of accuracy. So as I said, there is less concern about winds using RTK. I talked about the compass and the exact position resulting in more accurate hovering. There are a number of different GPS standards that the RTK base station supports, and those are listed here below. So it does take a while for this thing to lock on, sometimes 15 or 30 minutes. It's got its own little battery here, and this is the GPS antenna. And basically, I just set it up in a parking lot several hundred feet away from where I'm operating. And that's generally the first thing I do because it does take so long to lock up. And it does need, obviously, a clear view of the sky to be able to do that. As long as there's line of sight to the tower and the aircraft, it's not an issue.
We see those same things, Paul, at with surveyors when they're out surveying a road or something like that. You'll see something on a tripod sitting way away from where the people are actually doing the surveying, and I assume that's and it's got that. It looks just like the picture you had up, so I assume that's what that's doing.
Exactly, exactly. And the surveyors have a little bit of a different application, right? I mean, they probably have these RTK devices that are much more accurate than what I have. I think they get down to like the millimeter level or something crazy like that, and they're very precise about where they put the tripod and all that kind of stuff. And there are actually, I didn't know about this until recently, but there are actually services that each state has, I guess, with cellular service, so that if you don't have a clear view of the sky, you can use an SD card in here, and I think a cellular modem to subscribe to a service which will give you the same accurate positioning without satellites.
We do have one question here about somebody wanted to know, do you have any suggestions on drone brands? There's so many out there now.
I do. And stand by. I've got some slides on that.
Okay.
And how are we doing for time? We got about an hour. Is that what we usually?
Yeah, that's correct. You're in good shape.
Okay, great. So I wanted to talk a little bit about the challenges and limitations of imaging in an uncontrolled environment, which of course I'm defining as outside when we're taking pictures of towers. And one of the things that I thought initially was, hey, I'm going to go in and take pictures of these transmission lines and give the customers accurate temperatures all the way up the line and to the antenna, and then we can come back a year later and see if anything changes. Wrong. Can't do that. After getting certified as a level 1 thermographer, one of the first things they teach you is that you can't do that outside in a uncontrolled environment. And the main reason for that, there's a number of reasons for that, but the main reason is the wind. It's the largest variable that we run into measuring temperatures on a tower. And a 3-mile-an-hour wind can actually cut the temperature reading in half. So basically, you don't know what's going on at the altitude that you're imaging at. I had some crazy thoughts about putting an anemometer, on the aircraft and saying, okay, I measured this, piece of the transmission line when the wind was 6 miles an hour. But, there's all kinds of errors there with, prop wash and other things affecting the wind speed. So basically, what I understood was don't even bother. You don't want to try and tell anybody what the temperature of a transmission line or an antenna is if it's outside. It's just meaningless. So really, it comes down to qualitative measurements, not quantitative measurements. And that doesn't really detract too much because, as you'll see, it's been very, very helpful in terms of diagnosing problems. The angle of image acquisition is also critical and requires the angle of at least 60 degrees from what you're trying to take a picture of. If you're perpendicular to it, it's really best. And of course, we talked about the emissivity values of different components and those producing dramatically different thermal indications. So, it's important to identify labels and other surface materials to avoid misunderstanding what you're seeing there in the visual image. Spot size ratio. So I talked a little bit about focal length, and I wanted to go into that a little bit more in this slide here. Spot size ratio is the ratio of the distance from the camera to the target compared to the size of the target. I happen to use a 19 millimeter lens. If you're into photography, you know that the shorter the focal length, the wider the view. So a 19 and 25 millimeter lens are considered kind of telephoto lenses in the thermal imaging world. You know, if I were measuring thermal images of a big solar array on the ground, I'd probably want something wider, like a 9 millimeter lens. But in this application, getting closer up in a higher resolution without actually flying that close to the transmission line, you want a 19 millimeter or 25 millimeter. I could have gone with the 25 millimeter, but that kind of limits what other things you can do with it, because it's just so tight of a view there. But basically, this is an example, a camera with a 13 millimeter lens, which is wider than what I have, will cover 12 inches from 155 feet distance. This will give you adequate resolution at that distance. So that kind of gives you a reference. So people were asking about what I use, and I use DJI, of course, everybody's heard of. They make consumer drones, they make professional drones. This model, the 210 RTK, we already talked about what RTK means, is used by law enforcement a lot for search and rescue, but it's also a well engineered and pretty redundant electronics for an aircraft that would be flying in an environment like high RF. I actually had this sent back and hardened by DJI so that it's well shielded for the type of application we're using here. It's got 2 batteries for redundancy and longer flight time. It's got dual payloads actually here. You can see 2 cameras here. This one here on the left is the Z30 camera, which is a visual imager, and this is the XT2 thermal camera that we use for the infrared imaging. Getting into a little more detail, the XT2 camera has actually got 2 cameras in it. It's got a 4K visual camera as well as a infrared camera. This one's a 19 millimeter, which is exactly the one that I have. The resolution is 640 by 480. Doesn't sound great. This is on the infrared side. Doesn't sound like great resolution, but it's actually a pretty high resolution camera where you're talking about infrared stuff. Usually if you get a less expensive one, like one of the snapshot cameras, or some of the ones that have become more popular for using with your cell phone, the resolution's in the 120 by 90 area or something like that, which is still very useful, but for various different reasons, it's very expensive to produce these higher resolution chips that detect infrared. The frame rate is also critical in terms of determining the price, really. 30 frames per second is much more expensive than 9 frames per second. Those are the 2 standards for taking video. And again, if you're thinking about getting one of these, whether it's this kind or a different kind, the spot image size is based on the sensor size and the focal length and the distance from target and the required resolution. All those things need to go into consideration before anybody invests money in one of these things. This camera itself, just to give you an idea, is about 15K, and that's just this part, not the drone or the other camera. So you can see it's not cheap to get into, but it's built very well, and it is pretty hardened in terms of immunity to RF. Radiometric images are JPEG images that have metadata built into them. Every single pixel has a temperature value assigned to it. And again, for the qualitative stuff, it's not so valuable, but for the quantitative stuff, like this image of a circuit breaker panel, it's very helpful because you can get exact temperatures and see if those temperatures are meeting or exceeding the specifications of the manufacturer. This is the other payload. This is the Z30 camera. Again, you look at the resolution and you say 640 by 480. Well, that doesn't sound very good, Paul. Well, it's okay. It's not it's not breaking any records. But what's really cool about this camera is that it's got a 30 times optical zoom, which is unheard of. And on top of that, a 6 times digital zoom. So you'll see that you can get some amazing pictures with this, considering that it is gyroscopically stabilized. It's only a 2.13 megapixel sensor, but you'll see where that gets us in a minute. This is some of the hardware that I use on the ground. There's a separate display and a separate controller here. Both have their own batteries, and they pretty much last all day. And this is kind of what the typical flight deck looks like when I'm about ready to do a mission. Take the safety stuff very seriously. Before I got into this, doing it commercially at all, I was out in the desert and taking some great pictures and thought I would be really cool and catch my DJI drone with my hand, and the prop hit my forehead, and I was walking around NAB for 3 days with a Band-Aid on my forehead. So I learned really quickly to respect rotating propellers on these things. So these are even bigger propellers than the smaller consumer type stuff. So we're really careful. We mark off the landing area. We use hard hats, safety vests, emergency numbers, first aid kit, the whole works. We just don't want to take any chances with this stuff. So here's an example of a night photo that I took. This is a cellular array at about 150 feet, and you can see the antennas are not warm, but the electronics show up really easily, showing that they are warmer than the rest of the environment. You can see this is the base of a tower, the ice bridge coming over on the right-hand side of the image. And you see the telephone pole below the ice bridge there with the transformer on it, and a few other things that are warmer than the rest of the environment. So just as an example, you can see this stuff pretty clearly in the thermal world. So this is something that I discovered for a client in Boston. Basically, they were taking VSWR hits on their transmitter tower, transmission line anyway, about once a month, and they couldn't figure out what was going on. And they looked at it with a TDR and a spectrum analyzer, and they could see all the flanges and the bullets, and everything looked fine. But every once in a while, they'd go take these hits. After a few months, they asked me to fly it, and I did. And I obtained this image on the left, which you can see is visually depicted also on the right. And you can see heating on that 8-inch transmission line there. Well, I said, boy, that doesn't look good. Is that a reflection, or what is that? And so I tackled it from a different angle, and I saw that the same thing. And then I came back a couple of days later and imaged it again, and I saw the same thing. And I didn't see this anywhere else on the transmission line. So it was a disaster waiting to happen, and it did. I told the client exactly where this was. It was at about 937 feet. They took it apart, and they found that this O-ring here was not installed properly, and it slipped down onto the Teflon insulator and caused this arcing every once in a while. And it wasn't consistent. It was just every once in a while it would arc. Well, they took apart the transmission line. They ended up having to replace about 150 feet of 8-inch rigid. So it was a good catch, and it's a great example of how thermal imaging can catch some things that electronics can't detect. This is the same picture that you saw in the previous slide, but I'm using different palettes to apply different contrasts to the same image. And I just wanted to show this to show that there are no right or wrong choices for color palettes, but using software, you can enhance the picture and see different things by applying these different color palettes. Basic requirements for image capture: focus, range, and distance. The thermogram, these are things that you really have to get right when you're capturing the image, because they can't be fixed in post-processing or in software. So the thermogram, the picture must be in focus. If you don't have focus, you don't have the resolution that you're going to need to see the thermal gradients. It has to be taken at the correct temperature range. You must be close enough to the target that you're attempting to evaluate. We talked about that a little bit before. And again, these things, if they're not done at the time of the image acquisition, they can't be corrected later in the software. So again, it's important to get the focus right, and some of these things can make it difficult to get good focus. If you're flying too high or too fast, or you're yawing the aircraft too aggressively, or the gimbal's not working right, or if you have high humidity, all these things can lead to problems with getting proper focus. So there's some things to be considered here when you're acquiring the image. I wanted to talk a little bit about post-processing, and this is an example of setting the range so that you can actually see what you're interested in seeing. The photo on the left, that big red one, is a picture of the tower that's unstretched. And if you stretch the image to get rid of some of the areas that you're not interested in, like the sky background, you can see that there is a thermal gradient there. And again, this is that same picture I showed you with the problem on the transmission line. You do this by adjusting sliders in the software so that you get rid of, you're looking at a much narrower range of temperatures rather than, trying to look at the sky and the tower, which doesn't give you much information about what you're looking for. So here's some fun examples of what we're looking at in terms of antennas. You can see on this thermal image down here, the yellow areas are warmer than the gray areas. And the manufacturer of the antenna can take a look at basically the pattern here and ensure that what you're seeing thermally is expected. They can tell you where the power dividers are inside the antenna behind the radomes. And of course, handheld examples. This is inside a building. We can get accurate temperatures here. We're showing different spots where we're seeing Teflon insulators that are cooler than the copper lines. And basically, you can do the calculations and look at the emissivity values and basically know exactly what the temperatures are. And these are examples of what you can come back and measure weeks or months later and see if there's been any change. We talked about the times to image here. Here's a visual image up top of just around dusk, and basically on the bottom, you see a thermal image at about that exact same time. That Z30 camera I was talking about can get some pretty incredible close-up pictures. This beacon is at about the 500-foot level on a guide tower in Andover, Massachusetts. And if I wanted to, I could read the barcode off the top of that thing. This cotter pin in a guy wire attachment point is at about 300 feet above the ground. So you can really get some nice detail there and see if anything is out of whack or needs adjustment. Again, this is the top of the tower where the pole attaches to the tower, the pole that supports the FM antenna in this case. And this picture on the right is just a close-up of one of the bolts that attaches it. And you can obviously see if it's loose or if there's any corrosion there. A couple more pictures of the Z30 camera. On the right here, you can see some electric tape that the tower crew used that the client didn't know about, so that they asked them to go back up there and fix that. That would have never been possible to see without a close-up inspection. And let's see, visual tower scan. This is a short video clip of this is the 4K camera that is on the XT2 payload. So this is the infrared payload, but using the visual camera, and you can see that the resolution is pretty darn good here because it's a 4K video. Not going to play the whole clip, but we'll get up to the taper in the tower and you'll see going through the FM antenna. It's kind of fun. This tower is in Needham, Massachusetts. It's used for FM and TV, and it's about 1,200 feet. Let's see. So this is toward the top here. This is a side mount UHF TV antenna. And we're coming to the top mount UHF in a second here. This is another FM station that's close to the top. They're at about 1,000 feet here, I would guess. Another side mount TV. And this is the dielectric TV UHF antenna. Okay. So we have the same thing here, and I'm not going to play the whole thing, but this is what we call a sequence file, and it is the same thing you saw before, but in an infrared. This was taken a few hours after sunset. And just to give you an idea of some of the reflections you'll see and some of the real thermal imaging that you'll see. The interesting thing about these sequence files is that they can be broken down into 30 JPEG images per second. And each of those, remember, each of those radiometric JPEG images have a temperature assigned to each pixel. Not that these temperatures, like I said, are meaningful because they're taken outside and it's windy, but all that data is there, you know, just to be compared. This is the taper in the tower. This is an ERI and FM antenna array that we're going through here. And I'll just run this a little bit more because I want to show you the hotspot that we looked at, which is right here. There's that hotspot that we noticed in the previous image. And I'll run this right up to the top here where I think we can see the dielectric antenna. So. Yeah, it's not letting me fast forward. You can see the beacon here. That's not an infrared beacon, but it is heating a little bit. And you can see these reflections here. So this is why it's really important to be able to image from different angles to understand whether you're seeing reflections or you're seeing actual heating going on. So typically what I do is I'd fly up, it's a triangular face tower. I'd fly up each of the three faces and get data from different angles. Kind of interesting, you can see the gradients with the blue and the orange and the yellow here showing the different temperatures. And we're just about at the top here. There's that FM antenna. We get into the side mount, and there's a power divider network in there. And then we get to the top pole antenna. And if you look carefully here, you can see the power dividers inside behind the radomes on this thing. So this is very very useful for understanding if the antenna is performing properly or not. Okay. So that's the end of my presentation. Drones can be used in many cases to perform all these things we've talked about. It's important to have the right certification, airspace requirements, all that kind of stuff. Most importantly, interpreting these infrared images requires an understanding how the heat transfer occurs and how cameras detect IR radiation in that spectrum. So the best weapon against misinterpretation is education, and getting the thermal imaging qualifications and certifications is a good thing to do. It's not hard to do, but it really can add to the understanding. These are some good resources. Of course, here's my email address. It's just paulshulins@gmail.com or paul@schulinsolutions.com. Infrared training, there's a couple of different places you can get that. Infraredtraining.com is a good place to start. The FLIR Tools software at www.flir.com is free software that you can use on any radiometric image taken from just about any camera, even your cell phone camera, and that's free software. And then there's a lot of great resources on YouTube from ITC and FLIR. Just put those names in the search bar and you'll come up with a lot of good stuff. And finally, I'd like to thank my instructor, Bill Schwan, who's a level 3 thermographer. The Infrared Training Center is where I got my training. I bought my equipment at Florida Drone Supply. Jim Stenberg from American Tower Corporation has been very supportive and has used me quite a bit for American Tower projects, as well as some support from Gary and Cindy Cavell, Jim Leifer at American Tower. And again, there's my contact information. So sorry, I'm a little bit over here, but let me pause. And if there's time, I'd be happy to try and answer any questions.
Yeah, I would think, Paul, that even without the thermal imaging, that type of a video that you made going up the tower would be very useful, especially for the annual tower inspection.
Yeah, exactly. And one of the really good things you can do with a drone, whether it's thermal or not, is before you have a tower climber go up there, shoot the tower and give them an idea of what's up there so that they, even if they've been up the tower before, things might have changed since the last time they've climbed. So those are great things to do, even with an inexpensive drone, just to be able to give the tower climber an idea of what they're up against.
Especially if you have a lot of renters, a lot of tenants on there, you can look at what their system looks like, and if there's a problem, you can actually show them before they call a crew in to go up and work on it.
Yeah, no, absolutely, absolutely. And a lot of towers are busy towers, and people, new tenants come on, and it doesn't always get documented the way it should be. So the drone can be a great tool in terms of capturing what's there, and maybe the tenant isn't doing what you expected the tenant to do. So the drone can show where their antennas are, and if there's anything that doesn't meet your installation requirements, it's easy to see.
We got one final question come up. Have you ever done this on an AM tower?
Nope, have not. I've only been at this for a year and a half or so, and I've never done it on an AM tower. Actually, haven't really thought about it too much, but I don't see any reason why it wouldn't work. You don't have transmission. I mean, I guess if you do have an FM tenant on a AM tower, you should be able to image it the same way as I've been imaging these TV and FM towers. So yeah,
You
never
might
done
have
it.
a flange that is corroded or something, and there might be a little problem right there that you could check.
Yeah.
John, your comments?
No, actually, no additional comments. Paul, we certainly appreciate the presentation day. It's quite informative, and know that you went to a lot of expense and a lot of training to ensure that you do it right. And that's an important thing today, especially when you're dealing with a lot of the broadcast facilities around the country. Thank you.
Oh, you're
Yes,
very welcome. Thank you for the opportunity. And again, there's my contact information. If anybody wants to jot it down and they have questions later, just feel free to email me, and I'll certainly respond.
okay, good. We sure appreciate it, and we appreciate everybody joining us today. And we real quick, like, if I can drop off of your trying to drop off your PowerPoint there. Oh, we'll just leave it like that. The remind you of the situation coming up for next month. We actually have Shane Tovin will be with us. Shane is with K-Love and Air One. He will be talking about planning and designing and installing audio over IP. There are a lot of stations now that are transitioning over to the actual using audio over IP. So this is one way that you can actually get some information about that. And then one other thing I'll mention to you that beginning May 5th, we'll be publishing a second weekly newsletter. We do a newsletter now, which is for broadcast engineering. We're actually going to start one on May 5th that will cover live audio. Maybe you run audio for your church or for concerts, or you might even be working in a recording studio. We found out that there was a lot of engineers that actually get involved with live audio. So we're actually going to start a second newsletter to address that. If you would like to be on that particular newsletter, then be sure to just drop me an email, and we can help you get that going. So with that, we'll go ahead and sign off for today, and thank everybody for being a part of our engineering webinar here, brought to you by the ABA Engineering Academy. Thank you so much.